Hello students, welcome to the class. We will continue our discussion with the geometrical optics. We have seen the reflection portion, now we will see the refraction portion. So, we are starting our discussion with refraction of light. Optical medium. Optical medium is what? Through which the light can pass. So, optical medium. Through which light can pass. Now you already understand that optical medium is through which light can pass. Whenever light passes from one optical medium to other optical medium, suppose here is medium 1, here is medium 2, light goes from one optical medium to other optical medium, this is the path of light, then it will bend either towards the normal or away from the normal. This is towards normal. This is away from normal. This phenomenon of bending of light is called refraction of light. This is called interface. योलाई हामीहरू interface भन्छु. That means the boundary separating the two optical medium. One optical medium is different from other optical medium due to a property known as refractive index. So एउटा कुरा आयो refractive index. We will represent it by a symbol mu. यो mu symbol हो. Now what I would like to tell you, here the angle of incidence is there. This is the angle of refraction, not reflection, refraction, or angle of refraction. And this phenomenon of bending of light towards the normal or away from the normal is called refraction of light. So refraction is the bending phenomenon of light when light goes from one optical medium to other optical medium. The cause of refraction is basically the change in speed of light. So in the process of refraction, what changes? The velocity of light changes, velocity changes, wavelength changes, and frequency does not change. When light goes from one optical medium to other optical medium, its velocity changes, speed also changes. Speed also changes. Speed changes, velocity changes, wavelength changes, and frequency does not change. Why frequency does not change? Because it depends upon the source of light. So this phenomenon, when there is a term called denser medium, if the light is bending towards the normal, that means this medium is denser, and if towards the normal. If the light is moving away from the normal, then that is called rarer. Now the same matter can be explained in a proper way, that refraction is the phenomenon of bending of light when light goes from one optical medium to other optical medium. This phenomenon is known as refraction, angle of incidence, and angle of refraction. Light goes from rarer medium to denser medium, it bends towards the normal. Light goes from denser medium to rarer medium, it bends away from normal. Now the optical property of medium is refractive index. Refractive index. Now try to understand. If I am in air I can move in this way fastly, but up to this, suppose if I am inside the water, my speed will become slow. In the same way, in the denser medium, the speed of light is less. The medium is said to be denser if speed of light is less. Generally, in air or vacuum, the speed of light is 3 into 10 to the power 8 meter per second, and this is represented by c. Now, in any medium other than air or vacuum, the speed of light is less than this value. So, that is a denser medium. I was talking about the optical density. Optical density is basically refractive index. This tells about, this can be divided into two categories. One we call absolute refractive index. Another we call relative refractive index. Absolute refractive index symbol is in this way, mu A. What does it mean? It means refractive index of absolute refractive index of medium A. Here it is already understood that here it is air/vacuum. Air or vacuum is there. This need not to be written. If I say that refractive index of medium X is equals to suppose 1.5, then it should be already understood that it is with respect to air or vacuum. This is with respect to air or vacuum. This is the absolute refractive index. So, absolute refractive index को definition के छा absolute refractive index mu A is equals to C by VA. यो absolute refractive index को definition भयो. What does it mean? It means C speed of light in vacuum, that you already know, and V speed of light in medium A. यहाँ A medium था. So it should be speed of light in medium A. Naturally, what we observe that absolute refractive index, now see, whenever the value of V will be there, it will be less than C. So C is always greater than equal to V. So mu A is always greater than equal to 1. Numerator ठुलो छ, denominator सानो छ. So what we can observe? We can observe that the speed of light in vacuum is more than the speed of light in medium. What does it mean? Numerator is more, denominator is less. So absolute refractive index is always greater than 1. One more thing that you remember from your junior classes, that velocity is frequency into wavelength. So this can be written as frequency into wavelength air and frequency into wavelength medium A. As I told you, frequency does not change, so this FF will cancel and you are getting lambda air by lambda medium. What is lambda? Lambda is wavelength. So light is treated as wave, then it is the wavelength. So the refractive index is ratio of C by V, or it is the ratio of lambda air by lambda medium. This has to be understood very carefully. This absolute refractive index, this has got its value is always greater than 1, and it is unitless. dimensionless. It is unitless or dimensionless. This is your absolute refractive index. So this thing you all should know about the absolute refractive index. Now if we talk about the relative refractive index, this is representing relative refractive index, that is refractive index of medium A with respect to medium B. Refractive index of medium A with respect to medium B. Its value is, its definition is mu A by mu B. In terms of absolute refractive index, this is C by VA by C by VB. This is VB by VA. This is lambda B by lambda A. So you can use this as the definition. You can use this as the definition in terms of velocity, in terms of absolute refractive index. Relative refractive index is defined in terms of absolute refractive index, in terms of velocity in the two medium, in terms of wavelength. This is also unitless and dimensionless. And this absolute refractive index or relative refractive index, that is basically tells you the density. Now optical density is different from the density is equals to mass by volume. Here it is the speed of light that is being regulated by this factor, that is optical density. If optically denser medium is there, then the speed of light is less. If optically rarer medium is there, then the speed of light is more. One example numerical we can understand in this way. Example, if the refractive index of glass is 1.5, find the velocity of light in glass. This is the question, simple question. This can be understood in a very comfortable way. Mu glass is equals to C by V glass. So V glass is equals to 3 into 10 to the power 8 by mu, that is 1.5, that is 2 into 10 to the power 8 meter per second. This is the speed of light in medium glass. So this is the way we can understand. And in vacuum the speed of light is 3 into 10 to the power 8 meter per second. That value you should remember. After discussion of refractive index, we should understand the refraction through parallel sided glass slab. In parallel sided glass slab, here you see, here is the incident ray. It has bent towards the normal incident ray direction, and this is emergent ray. This is I, this is R, this is R, this is I, provided here also air, here also air. So this distance is basically D, and this is called lateral shift. This is called lateral shift. This angle is I, so this angle is I minus R. If we take the thickness to be T, then you see mu is the refractive index. Then you see O, A, B, C. Sine I minus R is equals to, if we drop a perpendicular here, this will also D, Bn. this is D perpendicular, so this is D. Sin I minus R perpendicular D by hypotenuse AB. So D is equals to AB sin I minus R. Take it as equation number 1. If we take the triangle AMB, then you see cos R is equals to AM by AB. AM is what? Thickness T by AB. So AB is equals to T by cos R. Therefore, D is equals to T by cos R sin I minus R. This is the expression for the lateral shift. One more thing you should understand, maximum value D maximum is equals to T when I is equals to 90 degree. When I is equals to 90 degree, then D maximum value of lateral shift can never exceed the thickness of the glass slab. So what is T? T is thickness of glass slab. Here you all should understand. If I ask a question that suppose angle of incidence is 60 degree, mu is equals to root 3, what is the value of R? R is equals to how much? Suppose this is the question. Then mu is equals to sin I by sin R. Snell's law, sin I by sin R. So mu is root 3, sin I is sin 60 by sin R, that is root 3 by 2 sin R. So sin R is equals to 1 by 2, that is sin 30 degree. So R is equals to 30 degree. This fact is basically a Snell's law that I will be discussing in detail. So mu is always in terms of velocity, also in terms of sin I and R. This fact is known as a Snell's law. A Snell's law of refraction. A Snell's law of refraction. This thing you all should understand. Now, the same matter can be represented by some other way also. The same question on lateral shift can be asked in some other way. What is that way? That also we will see. Now, what I would like to tell you, on the lateral shift itself, we would like to discuss a question. Suppose a ray of light is incident at an angle 60 degree on a parallel sided glass slab and covers a distance of 5 centimeter inside the glass slab of refractive index root 3. Then find the value of lateral shift. This is the question. Suppose This is the example that we have to discuss. Now, in this question, a parallel sided glass slab is there. This is the parallel sided glass slab. Thickness is not given. Ray of light is incident at an angle 60 degree. So normal is 60 degree. This is normal incident ray. After refraction, it covers a distance of 5 centimeter inside the glass slab, and then you have to find d is equals to how much. Here it is √3. Refractive index is given. A, B, C, capital D. This is the. Now, just now we have seen that lateral shift d is equals to t sine I minus r by cos r. So what we need? In order to find d, we need t, we need I that is already given, and we need r. So how can we find r? We can find r mu sine I by sine r, that is sine 60 degree by sine r. So just as in the earlier case, √3 by 2 sine r. So r is equals to 30 degree. We have got this value. In the earlier question also I have set this value. Now we have to find d. How to find d? This angle is your r, this is your thickness t. So cos r is equals to t by 5, base by hypotenuse. So 5 is equals to t by cos r. 5 is equals to t by cos r. Now in this equation I will keep this value. So what we can get? D is equals to 5 sine I is 60 minus r is 30 degree. That is 5 into sine 30 degree, 5 into 1 by 2, that is 2.5 centimeter. So in this case the lateral shift is 2.5 centimeter. This question will also help you in clarifying the concept of lateral shift. Now try to understand. We have seen mu is equals to B A, relative refractive index, mu B by mu A, that is equals to VA by VB, that is equals to lambda A by lambda B. This we have already seen. If wavelength is given, then also we can find. If velocity is given in the two medium, then also we can find. This is medium, this represents, this is your B and A represents optical medium. Now the question arises, in the process of refraction we have applied in this way. Suppose this is denser, this is rarer, just 1 minute, rarer, denser, I, R. Snell's law says that sine I by sine R is constant, and this constant is basically refractive index of denser medium with respect to rarer. Try to understand. This is Snell's law of refraction, and if this is meant to fall on a plane mirror, then for normal incidence case it will retrace its path. So for returning ray, if we want to understand the returning ray, then refractive index of rarer with respect to denser is equals to sine r by sine I for returning ray. So what we are getting a important result, r mu d into d mu r is equals to sine I by sine r into sine r by sine I. This will cancel and you are getting 1. Refractive index of denser, so refractive index of denser with respect to rarer, refractive index of rarer with respect to denser. Try to understand. That means in general a mu b, if refractive index of b is given with respect to a, then it is 1 by b mu a. This is a very important relation that you all should know. But what I would like to tell you, Snell's law should be not remembered in this way. This will create confusion. Snell's law should be remembered in this way, that this medium, its angle and its refractive index, its angle and its refractive index. That means you have to remember mu r sine I is equals to mu d sine r is equals to, this way you have to remember the Snell's law. For two medium it is okay, but if there are a number of medium, then this can be generalized also. What is that? If there are a number of medium in this way, light is going here, bending in this way, going here, bending in this way, going here, bending in this way, we don't know. We only know this thing, that this is mu 1, this is theta 1, this is theta 2, this is theta 2, this is theta 3, this is theta 3, this is theta 4, this is theta 4, and this is theta 5. Suppose mu 1, mu 2, mu 3, mu 4, mu 5. These are the absolute refractive index of first medium, second medium, third medium, fourth medium, fifth medium, and so on, whatever is the value. Snell's law generally says, what does the general statement of Snell's law is that mu sine theta is equals to constant. This is the general form of Snell's law. What does it mean? It means mu 1 sine theta 1 is equals to mu 2 sine theta 2 is equals to mu 3 sine theta 3 is equals to mu 4 sine theta 4, and so on. And this is equals to constant. This is the general form of Snell's law, and if you remember in this way, like PV diagram in heat, PV is equals to constant, then it is easier to use Snell's law and apply Snell's law in different questions. So this is your Snell's law in general form situation. When there are a number of medium present, then we can apply this form of Snell's law. Now one example I can give you on the same. If you remember this concept, the example will become very simple, otherwise it will appear difficult. Virtually it is difficult, really it is not difficult. Example is in this way. Example is in this way. So many medium are there. So many medium are there. Here the refractive index is given 1.6 and I is given 30 degree, and the ray of light is passing here, 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 and ultimately it becomes parallel to the last interface, and you have to find mu medium is equals to how much. This is the question. Different media are there, 1, 2, 3, 4, like that, and this is your mu m. Mu m is the medium. Now in this situation we want to apply the same Snell's law. What is that? Mu sine theta is equals to constant. That means mu into sine theta, mu first into sine theta 1, mu last into sine theta last. Mu 1 is your 1.6, sine theta 1 is your sine 30 degree, mu last that is mu m, and sine theta last is sine 90 degree. So what we are getting? Mu medium is equals to 1.6 into sine 30 is 1 by 2, that is 0.8. So we are getting mu medium is 0.8. If you know this formula, then it is very easier for you to solve this problem. Otherwise it may appear difficult. So this is one of the application of Snell's law in the general form. This is the general format of your Snell's law. Snell's law of refraction. So after discussion of Snell's law, we have to understand some more concept regarding the refractive index only. Refractive index, you all know, mu is equals to real depth by apparent depth. This is also a formula that everybody knows. Its proof is also required, very simple, and the concept is also has to be understood. Now you see, if I am taking in this way a vessel which is filled with some liquid, say water, of refractive index mu, and above there is air, and here is a coin, and this is viewed from normally above. Normally above, mind it, I am using a word normally above. Then here the ray will go, and as it is there, it will go here. So its image will be somewhere. This is object, this is image. This is the ray. This is mu. This is A, O, I. This point we take as M. AO is called real depth. AI is called apparent depth. AO is called real depth and AI is called apparent depth. So mu is equals to AO by AI. You should know that here AO is greater than AI. What does it mean? If you observe the coin from normally above, then this coin will appear at this particular point. Mind it, this is for nearly normal vision. What does it mean? These are paraxial rays, very near to this axis, very near to this axis. I am giving you a thinking process. Think what will happen if this is not paraxial ray. If I am observing in this way, if I observe in this way, then what will happen? Think on this issue and we will discuss it in the next class. So, in this situation, here air is there. What is the refractive index of air? 1. This is angle of incidence, this is angle of refraction, this is corresponding angle, so this is R, this is angle of incidence, alternate angle, so this is also I. Now I am trying to move towards the proof of this one. Now you see, I am applying the Snell's law in general form, so mu into sin I is equals to mu air into sin R. Mu into sin I is equals to mu air into sin R. Mu of sin, mu of sin. Now I have supposed that it is paraxial ray and I have given you the homework to search and think what will happen if it is not a paraxial ray. If it is not a paraxial ray, then what will happen and where the image will be formed. So if I talk about the paraxial ray, then mu, then I and R are very small. So sin I is approximately equals to tan I is equals to, tan I is how much? AM by AO. AM by AO. And sin R is equals to tan R. Sin R is equals to tan R is equals to AM by AI. So mu into AM by AO is equals to mu air 1 into AM by AI. AM will cancel, mu is equals to AO by AI. And what is AO? AO is your real depth by apparent depth. So we have got this formula, mu is equals to real depth by apparent depth. Many numericals can be framed on it, and this is also the formula of mu is equals to real depth by apparent depth. Suppose here object is in denser medium and at the same time here is the observer is in rarer medium. It may happen that suppose here is a pool of water, swimming pool is there, here is some fish and it is observing a bird here. So ray of light will go in this way, it will bend and ultimately you will be getting the image here. So object is here, image is here, this is A, and refractive index is same mu. In this case, here is the observer in denser medium and object is in rarer medium. So what we can get? We can get in this way, the same formula becomes mu is equals to apparent height, mu of this medium, denser medium, apparent height by real height. So apparent height is AI by AO, and here you see AI is greater than AO. So if the observer is in denser medium, then we have to apply this formula. That means if you will observe from denser medium, the object which is here, it will appear somewhere here. With this, I am ending the today's class. Hope you might have understood it, and in the next class we will try to continue the same discussion for our better understanding. Goodbye.